AQA A-level chemistry topic 5, completely patterned. Yeah, this is all of kinetics. Yeah, let's get into it. Collision theory. Yeah, so for two molecules to react, the correct part of the molecule must collide. Yeah, so obviously, if the OH is trying to react with the, I don't know, H of another molecule, yeah, the OH has to collide with the H. It wouldn't make sense for the OH to collide with another part like the C. Yeah. So yeah, and the molecules must collide with enough energy to react. Yeah, so it has to have enough the activation energy. It has to have enough energy to react. Yeah, and also at the same time has to be the same area. Yeah, so the steric factor quantifies how much the molecular geometry. So basically saying that steric factor basically talks about like the actual like orientation, of the molecule and which which part has to collide with which part and whatnot and why that's important. Activation energy is the minimum energy required for the reaction to occur as used to break bonds in the reaction in the reactants. Yeah. Maxwell-Boltzmann distribution. So you can look at the particles naturally for anything, right? And they all follow this similar type of distribution. Yeah. So zero molecules have zero energy, so no molecules would have no energy. Does that make sense? Yeah. There would be no molecules that would have no energy. Everything has energy unless you're at like absolute zero, yeah, where nothing's moving, yeah. But apart from that, all molecules have some level of energy, so it would never be at zero zero. Most probable energy, unless you were trying to say that no energy, like no molecules had no energy. That's what I'm saying. So the most probable energy, yeah, is the top of the graph because deep what the graph is saying. The x-axis is kinetic energy, yeah? So the higher up you go on the x-axis, yeah, the more energy there is. And the higher up you go on the y-axis, the more molecules. So around this energy down here where my mouse is, yeah, this is the most probable because all the molecules, that's where the most molecules are, yeah? So the most molecules, number of molecules is the highest here. So most molecules are at this energy. That's the probable energy, yeah? The mean energy, the average energy of the molecules here is slightly after that, yeah. The reason it's slightly after that, yeah, is because the mean will be a little bit higher, right, in terms of energy. And this is roughly where like number of molecules kind of like evens out. If that makes sense, yeah. The activation energy is all the way near the end, yeah. It doesn't matter where you put it, it has to be like somewhere near the end, yeah. And that's because not a lot of molecules actually react here when they collide, yeah. It takes a lot of energy, activation energy, for it to actually react here. So anything in this area where my mouse is now, this is the area where successful collisions occur, yeah. So this is the area where things actually react, yeah, because there are more energy than activation energy. The activation energy is here. Anything here would have more energy than activation energy, yeah. And the area under the graph is the total number of particles, yeah. So no molecules have zero energy. The area under the graph gives a total number of molecules. This stays constant, yeah, it doesn't change. And the graph is asymptotic on the right. So it suggests that there is a small possibility of having a very high energy molecule here. What that means here is an asymptote here means that something will get closer and closer to an axis here, but never touch it. So for example, here, as you see, it's getting closer and closer to the x-axis here, but will never touch it. That's because there's always going to be like a very small probability here that that the energy has an even higher, that the molecule has an even higher energy, right? And it can keep on going, 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 yeah. And this brother Boltzmann, yeah, allegedly in it, allegedly, yeah, that's what's take this with a grain of salt in it. That's what a teacher told me, yeah. Apparently, like, his brother in it, he had like no one like believed him back in the day in it when he had his theories and whatnot, second law of thermodynamics, all of that, yeah. No one believed him for any of it. No one proved it to him. Apparently, he asked his kids and that, not kids, his classroom, yeah, his classroom. Apparently, asked the classroom like if you had like air particles in a room, yeah, would it be able to like go to like would all air particles in a room only be on one side of the room? Yeah, because deep if there's one air particle in a room, yeah, it makes sense that air particle could be on only one side of the room, right? Now if there's two, there's still probability. It decreases the probability, right? But there's still a chance that both of those particles could be on one side of the room as well. Yeah. And so he asked his class this year, and he didn't like the response that he got from his class in it, and apparently that triggered his suicide. So then he killed himself after, allegedly. In it, allegedly, that story obviously sounds hella exaggerated, yeah. But he did kill himself, yeah, and he did ask his class that, but obviously he had other issues as well because no one believed him and shit. You know what I'm saying? So obviously he felt he was depressed and all of that, yeah. But that was like another thing that triggered it apparently because of the response from his class when he was asking that, yeah, because that question was driving him kind of insane because no one would believe him, right? And yeah, it's a bit mad. And after he died, yeah, always shit got proven. You know what I'm saying? And that's what it's kind of mad, innit? Always shit got proven after he died, man. So he died kind of like knowing that, like, you know what I'm saying, thinking he's a failure and shit. But yeah, he became known as like the father of thermodynamics and that as well. Anyway, temperature, yeah. So with temperature, yeah, the Maxwell-Boltzmann distribution, yeah, it broadens out a bit. So you see the top here, at T, yeah, it's bare like sharp, and then T plus 10, it broadens out a bit and it shifts to the right. Does that make sense? It shifts to the right and it broadens out a bit. Now look where EA is, activation energy, yeah? With the blue one, there's barely any particles underneath. Yeah, so barely any particles made it. With the higher temperature, it makes more sense. Higher temperature, more energy, yeah, converted into kinetic energy, yeah. So therefore, there's going to be more activation energy, yeah. More particles above the activation energy, yeah. So that's why the graph shifts to the right. It shifts to the right, yeah. So now look how many is under red. Yeah, there's bare particles under red, yeah, which means that bare particles made it over the activation energy at higher temperature, yeah, which makes more sense, yeah. The Maxwell-Boltzmann distribution shifts to the right so that a greater portion of molecules have energy greater or equal to the activation energy. The tip also broadens here as there's more thermal energy is transferred to kinetic energy and hence the molecules move faster and further, yeah? This leads to more successful collisions, yeah? Always you need to say successful collisions, not just more collisions, because it could collide, yeah, and nothing can happen in it. So you need to put more successful collisions, yeah? Concentration. Increasing the concentration of the solution, yeah, increases the number of collisions, yeah, between reactants. Hence, there will be more successful collisions, yeah, and the rate will increase deeper. If you've got more general collisions, yeah, then there will be more successful collisions because you're increasing the probability, yeah. Not by much here, but it is what it is, isn't it? Because the graph doesn't shift necessarily here. It's still staying the same. But because it has a higher concentration, the graph's now taller in that sense, yeah, and has more particles in that sense. So that's why it increases it a little bit above activation energy, yeah. Calm. Pressure. Increasing pressure decreases the volume of a gas, yeah? Obviously, like let's say you got a container down here, yeah? And you increase the pressure by pushing this down. Now the volume is smaller, yeah? So increasing pressure decreases volume, yeah? So hence, the molecules that are closer together and will collide more often. So if I increase pressure, yeah, the volume decreases. So if the volume decreases, yeah, the molecules are now closer together, yeah, and will collide more often. Hence, there's going to be more successful collisions and the rate increases. So the Maxwell-Boltzmann distribution will shift to the right, yeah, in a similar way to like the temperature, yeah. And by the way, the reason why the tip broadens, yeah, I didn't explain that, yeah. The reason why the tip broadens is because now there's a higher range at a higher temperature. There's a higher range between them because they have more energy. There's a higher range around this higher energy peak, right? Whereas before it was just like some particles had a lot of energy. Now it's a lot more particles have a high energy. Calm. Catalyst. So a catalyst increases the rate of reaction, yeah, without being used up. It provides an alternative reaction pathway that requires a lower activation energy, yeah. The Maxwell-Boltzmann distribution is unchanged in shape, but the activation energy is shifted to the left. So the actual like the distribution stays the same, yeah. But what the catalyst does is it moves its activation energy. You see with no catalyst, it's over here. It pushes that back here. So now there's bare like particles that can now react here. So more particles can react. The catalyst is now pushes it all the way back here. So now a lot more particles are bigger than activation energy here. And that's it, bro.